Hello, my name is Awais. In this video, we will be discussing about behavioral modeling in Verilog and synthesis into an hardware. We will be discussing what is behavioral modeling in Verilog, how we can write a behavioral modeling, what are the syntax and the rules of behavioral modeling, and also we will discuss why we are doing synthesis of behavioral modeling and how we will be doing as synthesis. So, behavioral modeling describes the circuit functionality using an high level algorithm constructs like always and initial blocks. This modeling focuses on what a circuit should perform rather than how. It is used to design both combinational and sequential logic and provide high level of abstraction, allowing a designer to write code based on the circuit functionality and not on hardware base. These are the syntax and rules of behavioral modeling. We can use always blocks for combination circuit and positive edge insert and always block for triggering in sequential circuit. Use of if else case for begin end. A reg keyword for output assigned inside always block. Example, here in always block I am using an if statement with a condition of select. So if condition is satisfied, which is select is enabled or high, we will be assigning y is equals to be here y is an output, so y should be reg. Similarly else y is equals to a, and then let's see an example of in Verilog code. So this is an example of an ALU written in Verilog code. Here we have declared inputs and outputs and the always block. We have not used any clock, so we will be triggering all the inputs, and we have defined and carry and result, so it is default will be 0, and then we have used case statement in which the select is ALU select. So when select is 0, we'll be doing addition, and then if select is 1, we will be doing XOR operation. If select is 2, we will be doing AND operation. If select is 3, we will be doing OR operation. If select is 4, we will be doing an invert. We can declare more expressions also. So the default value of result will be 0. Now we will try to synthesize it, but before trying, we will see what is synthesis and how we will be doing synthesis. How a behavioral modeling is translated into an hardware. So there are some steps for doing the synthesis, which is behavioral modeling which translated into an hardware only. So the first step is parsing and elaboration, then RTL generation, then optimization, technology mapping, and then we will be generating a gate level netlist. So the parsing, in parsing the tool reads and interprets an RTL code. It checks the syntax of an RTL code. It expands the module, resolves parameter, unroll, generate blocks, and many such things. It tries to convert an behavioral code which we have written into an boolean expression. So the tool does not just read it, it understands and meaning and builds an internal data model of reg wires on operators.
Now we will do write underscore
The next step is
ALU
after parsing elaboration,
synth
RTL generation.
dash
It converts the behavioral
block V.
RTL into an internal form, typically
So
netlist
it
of
has-
logic
it
expression.
says
It is
that
not a complete
it is
gate level
done.
netlist,
So
but it
now
will be having
we'll
an
go
boolean expressions in it.
and check
This
that
stage
file.
identifies the combinational and sequential elements, builds a logic equation for each
So
input,
an
outputs,
ALU
registers like that.
synthesis file has been set.
Then
This
we have optimization. Before
So now
technology mapping,
have
we
a
will be
map in
we try
library.
to
So
optimize the circuit. We performs Boolean algebra
File
simplifications.
which we get
We
from the
try to
synthesis tool
remove the
is
redundant
based
logics
completely on Boolean
and merge
expressions.
and
So we
equivalent
can say
signals.
here that ALU
After
select
that, we will be doing a technology mapping.
and
In this, we will
everything.
be
These are the
mapping
nets,
a Liberty
and
file
all these
in
are
which we
in
will
a
be
Boolean
getting a
expression.
hardware based on
So
that on the
actually we can't
Liberty
able to
file.
understand this. So we
Standard
will be
cell
doing more
library
synthesis. We
with
will be doing technology
we'll
mapping.
be having
So we can make
cell delay area
an
power
easy
information in that.
understanding. So for that,
Next, we will
first
be
we'll
also do after technology
see
we
this
can
stat.
we can do a time driving
Okay,
optimization
then
using the
show.
technology mapping files only some
Okay,
SDC
so
files. In that we will be having and setup
we
and
can
hold
see
times
here
all that. Then we'll generate a netlist.
how a synthesis tool has
In
made
netlist we
a
will be
block
getting a
diagram
gate level netlist which will be
of an
having all
ALU.
the gates flip flops
Okay,
only in that, which will be completely an hardware. So there are some synthesis tool, Yosys, which is an open source, then Synopsys Design Compiler, and Cadence Genus. These are the industry commercial tools. Let us see a synthesis in Yosys, how we can do in Yosys in open source tool. So now we will do Yosys synthesis of that ALU. So we'll go to the directory where I have saved the ALU file. Then I will open Yosys using the Yosys command. So the Yosys open synthesis suite is opened. Now I will do read Verilog ALU.v. This command is used for reading the Verilog file. So here it says that parsing Verilog input from ALU.v, then generating RTL-IL representation for module and successfully finished. So now we will be doing an optimization first. So the optimization has been finished. Then we will be doing synth for synthesis. So the synthesis has been completed. Now we will do write underscore verilog ALU as synth dash 1 dot v. So it says that it is done. So now we'll go and check that file. Okay, so an ALU synthesis file has been set. This okay. So now we haven't mapped any library. So the file which we get from the synthesis tool is based completely on Boolean expressions. So we can say here that ALU select and everything. These are the nets, and all these are in a Boolean expression. So actually we can't able to understand this. So we'll be doing more synthesis. We will be doing a technology mapping so we can make an easy understanding. So for that, first we'll see the stat. Okay, then show. Okay, so we can see here how a synthesis tool has made a block diagram of an ALU. Okay, now we will map an Sky 130 library in this by using ABC command, in which we will be write ABC dash liberty and Sky 130 library name dot lib. After doing this, we can say that don't call ABC, there is nothing to map because I have already mapped this. After that, we can also use stat. Now we can see that our components are changed into an realistic hardware, which is all from the Sky 130 library. Oh, we can also see using show command. Okay, now here we will be seeing all NOR gate, XNOR gate, NAND gate, clock inverter, like that. So actually we just want a gate level netlist. So we'll do ALU underscore gate level dot v. After this we can see a gate level netlist. So wires and all. Okay. So we have generated gate level netlist, which is from Sky 130 library, having AND, NAND, all these. This is called a gate level netlist, and after behavioral modeling, we will be doing synthesis and generating this gate level netlist. Then we can proceed to the physical designing using this gate level netlist. So thank you.